come from stars opposite the intruder at impact. Again, we see the stars on the lower right side of the primary at impact, which are already moving toward the intruder, are accelerated and become the high-velocity stars moving up and to the left. Here the orbital plane is perpendicular to the screen. We've already seen this as a third model in the first series. From here we see a pronounced splash effect with material closest to the intruder getting thrown up to the top. We see the importance of perspective if we remember that the model viewed from 45 degrees showed a much less well-defined major arm. One new feature emerges in this model. If we watch the material on the left side falling back toward the center of the primary, we see that it begins to form a short secondary tail running under and to the left of the central region. We again have the orbital plane tipped at 45 degrees, but now the intruder is moving in the same direction as the stars. As the intruder approaches, we see material on the right-hand side being decelerated and falling inward. The disturbance to the primary has become much more dramatic. For the first time, we see the intruder carrying material away with it. Stars opposite the intruder at impact move to form the end of the major tail, while stars from the upper left, which have been continually decelerated by the intruder, move to form the inner part of this tail. Finally, we have the intruder moving prograde in the plane of the screen. As the intruder moves into the primary, we see a wake of stars crisscrossing behind it. Some of those crossing from outside have actually been accelerated into retrograde orbits and are seen reappearing on the opposite side. Now the end of the major tail is formed by stars from the upper left at impact, while the middle and inner parts of the arm are formed by stars from the lower left and upper right sides. In the final series, we want to see what happens when we vary the mass ratio. We return to our original viewing angle. The perigalactic distance is 1 unit and the orbital plane perpendicular to the galactic plane. In this first model, the intruder is 1/8 as massive as a primary galaxy. All we get is a suggestion of a wave propagating partway out and a loose series of concentric rings in the center. The region just outside of the rings is somewhat deficient in stars. The outermost stars in the galaxy have not been noticeably disturbed. Observing this model, a tentative conclusion which we can reach is that the formation of a ring galaxy requires not only nearly central encounter, but also a mass ratio greater than 1/8. Here we have returned to a mass ratio of 1/2, our original model. We've increased the scale 2 1/2 times to compare with the model following. Remember that for this model, much of the material in the ring remained with the primary. When we have the masses of the two galaxies equal, the effect is somewhat different. The material moving out still forms a circular structure, but now all of it is being ejected from the primary. Furthermore, the circular structure never forms the sharply defined ring which we saw in the previous model and in the photographs. The disturbance to the primary has been too great to yield the ring structure we observe. This gives us some confidence in setting both bounds on the allowed intruder mass for ring formation. Apparently, its mass must be in the range of 1/8 to equal that of the primary. In this final model, the intruder is 10 times as massive as the primary. We see the primary drawn in at impact, and then it literally explodes. Just after impact, we see a stream of stars funneling down onto the intruder. What remains of the primary galaxy is the small cluster of stars moving off to the right center of the screen. We repeat the model at twice the scale just used. The interest in this model lies mostly in its visual appeal. In a real encounter, light from the massive intruder will probably wash out the contribution from the primary.